All right. Hello, everyone, and welcome to our webinar today. Sorry, we've had a little bit of a technical difficulties, but I think we've got everything back on track. I'm John Ricco, Executive Director of the APA, and our webinar today is energy efficient envelopes using insulated wall panels. So I thank you all for being here for today and for participating. Before we go ahead and get into the webinar itself, just want to touch on a few upcoming events and some informational items. First and foremost, we have our upcoming spring workshop on ultra high performance concrete in Tacoma, Washington, April 3 through 6th. We've got great registration for that event, great sponsor support, so a great program. So if you've been thinking about it or on the fence, it's a little bit less than a month away. So we encourage you to check it out and come join us in Tacoma. It's sure to be a good time where you will learn a lot as well. So check that out on the APA website. In addition, this is just one way that you can earn continuing education credits if you have APA certifications, whether batch plant operator, quality control 1, or quality control 2 technician. So there's many ways for you to earn CE, and this is one of them. So I urge you to keep up with that and to check out the many ways to do that. One of which is our YouTube channel, where we have a lot of playlists as well as some of the archived webinars that we've done where you can earn continuing education credits. So go ahead and check out the other aspects of the YouTube channel when you have a few moments. And then finally, we always like to touch on some of the member benefits we have, one of which is a significant discount program through United Parcel Service to ship parcels nationwide and beyond. So if you're in the need for any of those services, I urge you to go to APA website and check that out. So with no further ado here, let's go ahead and begin this session. So I'm going to go ahead and pull up this and pull up Eric. And let's go ahead and get this kicked off. For those of you who are logged in via YouTube, you can submit questions via the chat function. So that should be a bar on the right-hand side of your screen. If you are not logged into a YouTube account, throughout the webinar, there'll be a pop-up with an email address where you can send questions if you'd like to submit them that way. And we'll go ahead and fire this up. We've got Eric Arvalo here from Leviat. He's a structural engineer with a bachelor's degree in civil engineering from Texas Tech University. He currently serves as a product application engineer for Leviat. And in that role, he contributes to a wide variety of construction projects. He offers design support for Leviat's diverse range of construction accessory products, including thermal mass, which provides solutions for concrete sandwich wall systems. So thank you, Eric, for being here today. And I'll go ahead and I'll turn it over to you.
Awesome. Thanks, John. So yeah, let's go ahead and get started with this webinar. Today, we'll be talking about energy efficient envelope design using insulated concrete sandwich wall panels. So a few notes before we jump into the main topic for today. This presentation is protected by US international copyright laws. So any reproduction, distribution, display, and use of this presentation without written permission of the speaker is prohibited. Some additional notes here for the AIA program that this presentation does cover. Leviat is registered with the American Institute of Architects Continuing Education Systems. So any credit earned on completion of this program will be reported to CES records for AIA members. Certificates of completion for non-AIA members are available upon request. This program is registered with the AIS/CES for continuing professional education. And as such, it does not include content that may be deemed or construed to be an approval or an endorsement by the AIA of any material of construction or any method or manner of handling, using, distributing, or dealing with any material or product. Any questions related to the specific materials, methods, and services can be addressed at the conclusion of this presentation. Any questions related to the actual presentation content, well, we can take as we go. So for the purpose and learning objectives for today, the main purpose of this presentation is going to be to provide the benefits of concrete sandwich panels. Just course, we should be able to look at the typical insulated concrete walls, the types of designs that are out there, their components, their thermal and moisture resistant properties, and where they are used. As far as learning objectives go, at the end of this program, you should be able to describe the different types of insulated concrete panels that are out there, their components, and their possible contributions to sustainability. You should be able to explain the difference between material and effective R values of an insulated concrete panel, list the various options that are out there for insulation connector materials, and relate the thermal and moisture resistance properties of concrete panels and the materials that ultimately contribute to these properties. So we'll get started here with a quick overview of the sandwich panels. And just as a general overview, there are several benefits to using concrete sandwich panels. One of those benefits is going to be the constructability and durability of the sandwich wall system. So instead of having multiple contractors come in to individually install the thermal layers, air barriers, vapor barriers, and then the concrete itself, this type of panel system is going to incorporate everything into one assembly and is going to provide a highly durable, impact resistant concrete that is going to outlast many other materials out there. And simply put, concrete is not going to corrode or warp or rust like other materials out there, making this option virtually maintenance free. Another great benefit of this is, of course, the energy efficiency. The rigid insulation center of the sandwich panel is going to ensure that the wall system provides a thermally efficient wall with higher effective R values. When it comes to this, the sandwich panel is going to provide superior thermal performance and energy savings when compared to other types of building materials. Also, it is important to note that a sandwich wall panel is categorized as a barrier wall system. And what this means is that the wall system is not going to require an air cavity to deal with any moisture drainage. So the combination of concrete and rigid insulation is going to create a wall that can be designed to resist air infiltration and moisture issues. And of course, we do have that aesthetic factor. So with the sandwich panel, there is a wide variety of aesthetic options that can be added to one side of the wall or both sides. You can add reveals, textures, brick or stone veneers, to name a few examples. Now, there are three main construction methods when it comes to making a concrete sandwich insulated panel. It's going to be here on the screen. You see a precast method, cast in place, and tilt up. For the precast method, of course, the wall panels are going to be cast in a plant away from the job site. And once the panels are finished and they have cured, then they are transported into the job site. For cast in place sandwich panels, these walls are cast using vertical removable forms. And again, once they cure, you can remove the forms and the wall is standing there in place. And for tilt up, the walls are cast on site using typically the floor slab as a casting surface. And then once they cure, they are erected into place. And now we're going to move on to construction and components of a sandwich wall system. And for this, I want to give a quick example of this is going to be a tilt-up application of how a sandwich wall system is typically constructed. For this, the first step is going to involve, of course, forming the panel geometry. And in this process, it does involve making sure that all the geometric properties, including doors, windows, any exterior reveals or patterns are included in this process. And then once this forming process is completed, then you do add the reinforcement required for this exterior fascia of the panel. And then you come in with the concrete and then you pour it in place. Immediately after that concrete pour is completed, is secreted, then you do want to come in with the rigid insulation material. And you want to do this step while the concrete is still wet. So you're wet setting the insulation and the connectors in place to ensure that whatever connectors you are using get adequate consolidation around the concrete. So once you do have that installation in place and the connectors are placed in there as well, and make sure consolidation is adequate, you do come in and vibrate the connectors in the installation again to make sure that the consolidation is is acceptable. And then once this happens, then you can again come in and repeat the process for that second layer of concrete. So you come in with the reinforcement. At this stage, you we'll also need to come in with any inserts for lifting the panel, anything in place. So you put that, and then the panel is ready for the second pour. And once that is poured, then the panel is allowed to cure. Once that cures, then it can be lifted into position, braced, and then the roof connections come in. So now we are going to move on into the different types of sandwich panels that can be found out there. Typically, a sandwich wall panel can be broken down into three main categories. It's going to be either a non-composite panel, a fully composite panel, or a partially composite panel system. When it comes to a non-composite panel configuration, as you see here on the screen, this is going to consist of a main structural width, which typically ends up being on the inside of the structure. And this main structural width is going to be designed to support all the applied loads, including supporting the exterior fascia of that panel system. Typically for a non-composite panel, it is designed so that the insulation connectors are ductile enough to allow for that fascia to expand and contract due to thermal expansion and contraction. So you do want to make sure that connectors are strong yet ductile enough for that flexibility and cyclical changes and thermal expansion and any other applicable loads that might influence the fascia width. And just in summary, a non-composite system is going to allow the exterior fascia to act independently from the interior structural width. When it comes to a fully composite panel, this type of panel is designed so that both the exterior concrete width and the interior concrete width act together to resist the applied loads. And typically, this type of system is a bit thinner and lighter than the non-composite panel due to the fact that you are able to use both of those concrete layers as strength sections for your wall system. The negative aspects of this is that to typically achieve a fully composite panel configuration, you do need a lot of stiffness support between those concrete layers, and this typically requires some type of solid sections cutting through that insulation. And once you do this, you are drastically lowering the efficiency of the panel as you are including now any thermal bridges into the insulation system. So when it comes here to a partially composite panel, this type of panel system takes all the benefits from a non-composite and a fully composite panel with a little bit of flexibility when it comes to the system. A partially composite panel is going to allow the designer to use the inside and the outside concrete widths, but due to the ductility and stiffness of whatever connector is connecting those two widths, you won't be able to achieve 100% composite action. And this is not necessarily a negative aspect to this, as for most of the applications out there, you don't really need 100% composite action. Somewhere in between is more than adequate to provide enough strength to that panel to have an acceptable design and also to support all the applied loads. And at the same time, you get the benefits of the ductility of the connector. So you are going to reduce thermal bowing concerns that you typically see with fully composite panels. And with the correct connector, it does allow you to use edge-to-edge insulation. And again, with that, you are reducing any thermal bridges that might happen with a fully composite panel. So So now we're going to switch over to briefly discuss about.
Hey, Eric.
Yes.
I don't know if you saw, but a question popped up via email that I put in the chat here. What types of structures benefit more from non-composite sandwich panels, and what types of structures benefit from partial composite panels?
Yes, I see this now. Yeah, so when it comes to a non-composite wall system, typically you do have that independent behavior between the exterior fascia and the interior concrete wire. And what this benefits is that in a typical climate condition where, let's say, you have your ambient temperature indoors, but very cold temperatures outside, that drastic difference in temperatures, you're going to prefer a non-composite system. That way, you have the internal concrete wire not being affected by the drastic changes on the outside. And it works vice versa too. Let's say you have a structure with a cold storage structure where you have very cold temperatures inside and very hot summers. Again, you have drastic differences in temperatures. You're going to prefer a non-composite system to allow that exterior fascia to expand and contract without really affecting the structural life. If you have a type of structure that maybe it's just a warehouse of room temperature, ambient temperatures, or maybe just cladding panels that are not really affected too much by drastic temperature changes, then that's typically going to be a partially composite or fully composite application. Okay, so now we're going to move on here to just briefly discussing the different types of insulation wire connectors that can be found out there. Historically, there has been a wide variety of wire connectors used in the sandwich panel industry. Some of these connectors are seen here on the screen. They're going to be metal connectors, plastic connectors. There's also different types of carbon fiber and fiberglass composite connectors as well. When it comes to the specific categories, metal connectors were the very first to be introduced into insulated panel construction. But due to their high conductivity, they do create a significant level of thermal bridges, which ultimately results in very high levels of energy loss, and it just makes them extremely difficult to meet strict energy code requirements nowadays. Other connectors, such as carbon fiber grid strips, these are going to be less conductive than metal connectors. We have to take into account too the mechanical properties of the connectors. Some of the connectors can be pretty brittle, must be handled very carefully to make sure that no damage is caused to the connectors. And also that additional stiffness that comes with these connectors can interfere with any thermal expansion and contraction of the concrete. Injection thermoplastic connectors are also out there. These types of connectors, again, low conductivity, and that you want to stay away from metal connectors. And you also want to make sure that the material properties are comparable to that of concrete. There's a lot of cyclic changes that can happen to that exterior fascia wise, and you want to make sure that the connector properties are adequate to that. We also have fiber composite connectors, such as the one you see here on the screen, the protruded method of manufacturing these connectors. Typically assumes that, or involves having continuous glass fibers that are dipped into a polymer resin mixture. And this mixture of the glass fibers with the resin are heated with a heated dye, and they're baked, essentially creating a very highly ductile yet very strong composite material. And with this type of configuration, you do get similar values comparable to concrete when it comes to strength and to thermal expansion coefficients.
Hey, Eric, it looks like we've had one more question while you're pausing right there pop up in YouTube. What are the biggest differences / advantages between insulated sandwich panels versus traditional precast panel with separate insulation?
Yeah, so when it comes to the main advantages of an insulated concrete panel is going to be mainly having to include less trades that go into the construction of this. When you have a sandwich panel, you have one trade that is doing the concrete insulation and the entire system into one. It's all done into one application. When it comes to having a traditional method, at the end of the day, based on the design, they could probably achieve very similar R values, but during that construction phase, during the time where it's critical to get things done at specific schedules, you're having to deal with more trades that come in to do the concrete and the trade that has to come in to do the insulation section. So it's just more scheduling concerns, more delays, more costs when it comes to doing traditionally versus uh, insulated panel that has all-in-one system made by one trade. I hope that answers that question, and we'll keep moving on here to the next slide. So here on the screen, you do see demonstration of the different effects that the wrong insulation connector can have. Here on the right, you do see this thermographic image showing metal connectors, and you do see all the thermal bridges that's going on here. It just ultimately creates a very inefficient panel, so it just defeats the purpose of having insulation in the center when all the thermal bridges still are creating a lot of energy loss. Here on the right, there's an example of a fiber composite connector system, where again, you have the connectors that are very low conductivity. It prevents energy loss, it prevents thermal bridges, and it allows for edge-to-edge insulation. And you clearly see the drastic effects of using the right connector versus the wrong connector.
Hey, and Eric, we've got one more, and you might, if you're going to touch on this, feel free to come back to it. But another question from YouTube: what connection devices are appropriate specifically for non-composite panels versus composite?
So when it comes to specific connection devices for a non-composite system, you want to have that independent behavior between the exterior fascia and the interior structural width. So you do want to select a connector that is strong enough to support the weight of the fascia, but ductile enough to resist any thermal expansion changes, any cyclical effects due to shrinkage, and this is, of course, year-round and for the entire lifetime of the structure. You do want a highly ductile connector to support those cyclical changes. When it comes to partially composite panels, you do want a stiffer connector. The stiffness is going to ultimately depend on the geometry of the connector, the material properties, but this is going to provide the composite action of the panel. So the stiffer the connector, the more composite action you get into the panel system. But if the connector itself is too stiff, then you start going into the fully composite boundary, and that's where you don't want to go too stiff, because then you start introducing panel bowing concerns into that mixture. So you want a good mixture of still stiffness but ductility to minimize thermal bowing concerns in a partially composite panel. Okay, moving on here to this next slide. And just briefly here, I want to touch on the different types of insulation that is typically used with insulated concrete panels. Typically, you do see EPS, XPS, and polyiso, and the selection of this insulation is going to depend on various factors. Um, Ultimately, all three of these types are great options for sandwich panels. It just depends on what R values you need, what type of vapor diffusion properties you do have in the system. Um, EPS is going to have the lowest R value out of these three types, followed by XPS, and then polyiso does have the highest rated R value. But again, there's a lot of different um, items that go into selecting this. There's price, there's R value requirements, there's moisture resistance properties. So it's very specific to the specific project you're working on. Now switching over here to the performance of the insulated sandwich panels. Let's see here. So as many of you are, of course, aware, most states have adopted energy codes based on ASHRAE, the ASHRAE standard 90.1 or IECC requirements, which are going to ultimately specify the thermal resistance of the building envelope. These requirements are going to be defined by the construction materials that you use in your project. It could be a mass wall, a steel stud wall, or wood wall, and the geographic location. So meeting or exceeding the R value requirements of these codes and the standards is going to affect the HVAC equipment sizing. It's going to contribute to points for green building rating programs such as LEED. And of course, it's going to improve the bottom line for the owner because the building is going to be a lot more efficient. And I'm touching up here on more detail regarding one of the questions that came up earlier. When you are designing the sandwich wall system, you have to realize that the placement of the installation is critical. In ASHRAE and the IECC, they do provide some values and requirements that are based on the insulation position in the mass wall. The three main locations when it comes to this are going to be, of course, placing insulation in the interior, placing insulation in the exterior, and then integrally insulated concrete mass wall. And when it comes to interior insulation, again, the things you have to consider are that another trade has to come in to install that insulation, but also you are losing that durable concrete surface that typically an insulated concrete sandwich panel does have. Um, when it comes to insulating from the outside, some of the things to consider with that is, again, that other trade that has to come into play, another additional step to consider, another cost to consider, and again, losing that durable surface on the outside. And then you have integrally insulated concrete panels where all the work is done on the ground by one tradesman. The insulation is protected from damage by two concrete layers, and then you do end up with a durable concrete surface externally and internally. So now we're going to switch gears to talking about nominal and effective R values. When you are considering a sandwich panel, it is going to be evident that the R value contribution mainly comes from that rigid insulation layer, as concrete is a very poor insulator. Per the energy code, this is going to be considered the insulative or the nominal R value, which is what the insulation alone provides. But the effective R value, that is defined as the overall thermal resistance of an assembly, and that is the value that matters the most. This value does take into account everything in the wall system. So it's going to consider not only the insulation alone, so the nominal R value, but it's going to consider the fasteners, any thermal bridges in that system, concrete edges, anything that composes the system itself. So here on the screen, we have a brief example of calculating an effective R value. And as you see here from the example in the last slide, 2 inches of continuous insulation is going to provide R value of 10. But if you do take into account all the components of the sandwich wall system, you do get additional contributions. So ultimately, the effective R value is going to be something like 11.3. So it is a greater R value provided by the wall system itself. Here on the screen, it's a screenshot of ASHRAE 19.1, and what this example here is showing is how the effective R value is going to be compared to the nominal R value of the continuous insulation. Um, for something like this, if we look at the box in blue compared to the box here in orange, you do see that for a mass wall, you would need an R value of 11.4 nominal. But if you look at the assembly equal based on the U value, you do need a U value of 0.09, which ultimately translates to 11.1. And what this is essentially showing is that if you consider the assembly maximum requirement versus the minimum insulative R value, you get more benefits using the assembly. You get a smaller requirement to meet. So if you're taking into consideration the assembly, you have to use less insulation to meet the requirement versus just nominal values where you might have to use thicker insulation, a higher rated insulation value, and that's going to be adding cost to your system.
Hey, Eric, we have one more question here that kind of came in. Do panel joints disrupt the continuously insulated envelope assumption?
Panel joints, this question does come up a lot because when you're using an insulated panel system, you can assume with the right connector that you're using edge-to-edge insulation. And that will be for the independent panel. So when you do have panel joints, let's say panel to panel, you have a gap there, that insulation is disrupted. But when typically these are being constructed, a panel to panel joint is going to be covered with closed cell foam backer rod and then with spray foam to fill out joint and then a proper sealant. And that allows the insulation to be considered as continuous, since you do have that rated R value proceed from one panel to the next through that sealed joint. Here, see another question.
Eric, that's more about our CEUs, so I'll respond to that one individually.
All right, perfect. Right, switching out to the next slide here. So something important to note here is that when you are using a mass wall, there is a lot of other benefits that do come into play, not just the assembly R value, but when it comes to insulating values, there are two primary values that are tied to the high mass system. And this is going to be the material R value and the performance R value. Due to the concrete's ability to retain heat and release it when temperatures fall, this is going to dampen the effect of that exterior temperature change on heating and cooling systems. And this is called the thermal mass effect. So essentially, the properties of concrete allow it to absorb energy when it's the highest, and when it gets cool, it allows it to release that energy. So there is a dampening effect that happens. It could be day to night or seasonal changes. That's a very great application when it comes to this. And due to this thermal mass effect, the performance R values of the wall system can be 2 to 3 times greater than that of the material R value alone. And this is ultimately going to result in energy savings up to 50% or more. And going back to this screenshot from ASHRAE, the thermal mass effect is something that is considered into the energy code analysis as well. And from this table, you do see that mass walls are often going to require the least amount of insulation to satisfy code as compared to other types of buildings, such as metal buildings, steel framed or wood framed. You do see that the assembly U value requirement, the higher the number, the better the least the requirement, and you see the mass wall is shown as the highest here, showing the most benefit due to that thermal mass effect. Now moving on to the topic of air infiltration. Sandwich panels are going to contribute to reducing both the vapor diffusion and the air infiltration. Vapor diffusion is basically the process by which water is going to migrate through the wall system, where each component in that wall system is going to contribute to moisture migration. Air infiltration is going to it can result in reduced thermal comfort, interference with the proper operation of mechanical ventilation systems, and it could damage the building envelope components. So it is important to note that anywhere from 20 to 50% of air leakage actually occurs through the wall system itself. So another benefit of an insulated concrete sandwich wall is that concrete thicknesses of 3 inches or greater can qualify as an air barrier because they have very low air permeance. Now, when it comes to the importance of analyzing the sandwich panel for moisture concerns, a dew point is something that is very important. So to confirm that the wall assembly you currently have, let's say it's a 434 concrete panel, if you want to make sure that there are no moisture issues within that configuration, designers should ask that a preliminary dew point analysis is performed and be included in the concrete contractor's submittal package. And a dew point analysis is going to calculate the point at which water vapor could condense within that given sandwich panel assembly. And this analysis can predict the condensation potential for certain wall systems under very specific climate conditions. Um, this dew point analysis is going to ultimately show if the operating temperature of the specific room type or the overall building type is going to remain above the dew point temperature at very strategic locations, such as within the exterior concrete layer. And this analysis is also a great preliminary tool that can allow the designer to select the proper insulation material, the proper insulation thickness for the specific building type, or for the specific operating temperature conditions.
Yeah, hey Eric, I just wanted to touch base on the questions that kind of popped up there. I think this is going back to that ASHRAE chart you were just showing on the previous slide. Why is the 3-inch thickness noted as a requirement for air barriers? And then the follow-up to that, when the trend is to go to thinner wall thicknesses.
The 3-inch thickness noted is not a requirement for air barriers. It's just a qualification that 3 inches of concrete can qualify as an air barrier. There are other methods of mitigating this type of issue. And again, this is something that the dew point analysis can provide. If you do run a dew point check and you see that there are any moisture concerns, anything that requires more mitigation applications, such as maybe a vapor barrier within that, then you can proceed accordingly. It's just an additional benefit that was added in there that if you do happen to have 3 inches or more, that qualifies as an air barrier resistance. And see, yeah, the trend to go to thinner and thinner wall thicknesses. Yeah, that's completely understandable. And that typically leads to doing partially composite systems where you are able to use both of the concrete whites as an addition to the strength of the panel. But again, based on the concrete properties, you can only go so thin depending on the applied loads, on the applied structure. You can have a very thin cladding panel, but you might not have the same benefits if it's a completely load-bearing panel and like a seismic condition, for example, where you do need that strength of concrete, and that comes with thickness as well. Okay, we're going to switch over here to just talking about a couple of applications where typically sandwich panels can be seen. Of course, the variability of this, they can be applied to pretty much any type of structure out there, but I just wanted to go over a couple of examples and benefits. For warehouse and distribution centers, this is a great example. These types of insulated panels are going to provide highly durable exterior and interior surfaces that are going to be resistant to forklift damage and vandalism. That's something that buildings go through. And just in summary, concrete sandwich panels are going to be a great low maintenance option for buildings that are prone to damage due to daily operations. Another great benefit is, of course, the speed of construction. By sandwiching that insulation between the two layers of concrete, then the facility's walls are built and insulated in one operation. So you're going to greatly reduce the construction time and you're going to get the facility up and running much faster. For beverage and low temperature distribution centers, these are going to be a natural fit for concrete sandwich panels because, again, you do have that thermal and moisture control that comes with a properly designed insulated panel. And this is going to keep the products inside at that optimal temperature, and it's going to be kept at, of course, the steady temperature year round through any operation that is assigned for. These buildings are also going to benefit from the same perks of having a strong interior and exterior surface. So again, you're going to have low maintenance on the structure and resistance to damage, to theft, to vandalism. So when it comes to healthcare and education facilities, these are going to be a great fit for concrete sandwich panels as well, especially when we talk about building expansions with, for example, precast sandwich panels. The perk of offsite construction can be extremely beneficial. You get fast direction times that allow for reduced straights and less disruptive construction sites. All of this, of course, is going a long way to ensure patient recovery and minimal noise levels in the classroom. And also, a properly designed sandwich wall envelope is going to ensure that the air quality is kept at optimal levels with constant operating temperatures, relative humidities, and no moisture or mold concerns due to that internal insulation system. And just to wrap up this presentation, the benefits of sandwich panels over traditional construction methods are going to be the sustainability, the speed of construction, the fact that you get an integrated wall assembly into one step, and the overall low maintenance application. Additionally, the wall can be designed to ensure that the dew point occurs in the exterior concrete layer and not within the building. And also with the proper sandwich panel connectors, edge-to-edge insulation will ensure that there are no critical thermal bridges in the envelope system. We also learned that due to that thermal mass effect of insulated concrete walls, the performance R value of this high performance system is going to be 2 to 3 times greater than that of the material R value alone. And this is going to create superior thermal efficiency. We learned that the attractiveness, the durability, and the thermal efficiency of concrete sandwich walls are going to allow this construction method to be found virtually on every type of structure out there, from residential buildings, schools, hospitals, low temperature facilities, warehouses, anything that requires controlled atmospheres. That's a great application for sandwich panels. And yeah, so this is going to conclude the CES portion of the program. So yeah, this is the end of this session.
Yeah. Hey, Eric, one more question that popped up here in the chat. And I would encourage if anyone else has any questions as we begin to wind this down, to please send them via email or chat. You mentioned edge-to-edge insulation as possible with insulated sandwich panels. Is that true for all three types, cast in place, precast, and tilt up?
Yes, with the proper insulation connector, you can allow for edge-to-edge insulation that is going to extend throughout the entire area of that concrete surface. Um, and again, this goes back to using the proper connector for non-composite applications, for cast in place, and for partially composite systems. You do want to minimize any concrete through zones, any use of metal connectors or welded wire girders that introduce thermal bridges. So if you get rid of that and choose a good, strong but ductile connector, you can have edge-to-edge insulation for any application.
Okay, great. Thank you. Let me just take a second here. I don't see any more in the chat. Let me just check email to see if any more came in that way. All right. No, I don't see any. We'll just give just one more moment here. Any last questions from the folks who are out there? All right. Well, we'll be sure to provide, if any do come in. Oh, wait, here's one. I hear architects talk about the fact that the sandwich panel insulation is in plane with the windows. Why is that important?
Typically, I'm not too familiar with the actual architectural detailing, but I would assume that it's based on the thermal proofing that they're doing at the windows. You do want to make sure that when you are following the cross section of the insulative plane, that everything is in line to make sure that the I guess the thermal break within that cross section is not disrupted by an offset insulation. That can be typically seen as well, for example, when it comes to creating a thermal break in balconies for, let's say, a very tall building. The balconies have a thermal break, and that thermal break has to be within that same wall system to not disrupt the thermal break level, and then ultimately you do end up with additional thermal bridges in that system. So I would assume that to avoid any breaking of that single line, you want to keep the windows within the insulation layer.
All right, great. Thank you, Eric. I do not see any other questions. So at this time, we'll go ahead and wrap this up. Eric, thank you very much for taking time to present today and to help educate our members on this topic. And thank you very much for being here and for participating.
Thanks, John, and thanks APA for this chance to give you guys a good webinar here.
All right. Thank you, everyone, for participating here today. I encourage you to go to the APA 2024 Spring Workshop website page on UHPC. It's going to be a great event, and we hope to see you all out there. So once again, thanks, Eric, and everyone. Have a great rest of your day. Bye, Eric.